Lecture number 12. We started doing volume on Monday's lecture. Now we're going to look at how to find the volume of solids of revolution. So what does this mean, to be a solid of revolution? Well, a solid of revolution is a plane region, a two-dimensional region, which for us will always be represented in the Cartesian plane, and it is rotated about some line. The line is called the axis of revolution. So visually, what we're working with here is we start off with some two-dimensional region in the Cartesian plane. Let's just check it out like this. For example, let's do a semicircle. And then you rotate it about some line. And usually, the line about which you rotate is denoted with a little looping arrow. So in this case, this line right here, which is the x-axis, this is the axis of revolution. We rotate this region, this two-dimensional region, about that line, right? So you take it and then just wrap it around. And when you do that, when you rotate this region about this axis of revolution, you go into the third dimension, you go along the z-axis, which we don't have to include, but I just did, right? Because you enter that third dimension, which on the xy plane turns into the xyz plane. And what you would get is a three-dimensional solid. It's solid because all of this space gives you a solid volume. So it's not just a shell. It's not just this line is being rotated and you have a hollow inside. This region is being rotated. And so you have a solid figure. And what it would look like in this case, when you rotate a semicircle about its center, it gives you a sphere. That's my sphere. Right, so as a solid of revolution, because you form the solid by rotating or revolving some two-dimensional plane region. And again, the word solid is there because this thing is solid. It is completely filled in because the region was filled in. Now there are a few techniques to find the volumes of these things. Let's first check out the disk method. We will learn three techniques to find the volume of various solids of revolution. Each of these three techniques is useful in one case or another. First, let's check out the disk method. First, random side note. You can spell disk in two different ways. As far as I'm aware, there's no difference, so feel free to use either of those. I'll probably go back and forth between those two spellings. I'm not like partial to one spelling. So what the disk method has is this is the method to use when your plane region that you are rotating is right up against the axis of revolution. So the axis of revolution is one of the boundaries of your two-dimensional region. So there is no gap. There is no gap between the plane region and the axis of revolution. For example, if I took this region and rotated it about this line down here, then there is a gap. All this space right here is a gap. There's a gap between my region and the axis of revolution, so you would not use the disk method for this. You only use the disk method when there is no gap between your region and the axis of revolution. So that's when you use it. Now let's figure out how this method works. Oh, one last quick note. You may wonder if the axis of revolution has to be horizontal, and the answer is no. The axis of revolution could be vertical. You could rotate by that line. Or it could be diagonal. You could rotate about this line, or it could be any curve. You could rotate the region about that curve. We will stick to horizontal and vertical axes of revolution in this class, but it could be anything. Okay, so let's figure out how the disk method works. So let's, as an example, so that we have some region that goes from A to B, and like here's the top of it, whatever. Right, this is our plane region. And we're going to rotate that about this axis of revolution. I actually made some visuals for this, which are somewhere. Huh. I seem to have lost my visuals. There we go. So, here we have a two-dimensional plane region, rotate about the x-axis, and it turns into this shape right there. So the problem with this is that there is no formula for that volume. Right? It's just like the area stuff. When we find the area of any plane region on the xy axis, there might not be a formula for that shape. There's no volume formula for that shape. And so what we do is very similar to what we did for area. We take our plane region and we approximate it with rectangles. So that right here is, we approximate the plane region with rectangles. And then we rotate that region, that approximation, about the axis of revolution. When we do that, it gives us this, which if you can see, this is a bunch of cylinders. Because when you rotate each rectangle about the axis of revolution, each rectangle becomes a cylinder. And the benefit to that is that we have that formula. We know the volume of a cylinder. So our game plan is to take our plane region, approximate it with rectangles, rotate those rectangles about the axis of revolution, and it'll give us a bunch of cylinders. Cylinders which approximate our volume. We use those cylinders to get an approximate volume, and then we take the limit as the number of cylinders goes to infinity. And as the number of cylinders increases, our shape becomes more and more like our true shape. And as you reach infinity, it becomes one and the same. So let's now turn this into a workable formula. So first off, we break our region up to a bunch of rectangles. Right, that is the approximation. Now let's just pick one of those rectangles. I'll pick this one. When we rotate that one rectangle about the axis of revolution, it's going to give us this. It's going to give us a cylinder, where this is the original rectangle. Right, that was rotated around. Since it's a cylinder, the volume of that one cylinder is pi r squared h. Right, and so essentially we'll call this V sub I. V sub I is the volume of the ith cylinder, because when you rotate these rectangles around the axis of revolution, you get a finite number of cylinders. This is the volume of the ith cylinder. And the volume of the ith cylinder is pi times the ith radius squared times the ith height. And then the overall volume, the volume of our shape, is approximately the sum of all these cylinders. So this is the volume of our entire region. It's the volume of this thing right here. That is V. And we approximate it by adding up the volumes of all those cylinders. So it's the sum from 1 to n of V sub I. Well, so V sub I is pi r sub I squared h sub I. H sub I is delta x, right? Because the height of this cylinder is that length right there. That is the length of the ith subinterval. It is delta x. It is the change in x from one rectangle to the next. R sub I is going to be a function of x. So we'll call it big R of x. We know it's a function of x because if we go back to our formula here, as you move down the x-axis, where you are on the x-axis determines what the radius is of that cylinder, right? Because the radius is based off the function, and the function is a function of x. So whatever the radius is, it's a function of x, which means that our true volume is approximately the sum from 1 to n of pi r of x sub I squared times delta x. Pi r squared x, because you're adding up all those cylinders. This is a Riemann sum. Because this sum has a function and then the change of the variable. You need that delta x to be a Riemann sum. We got it. Which means that the true volume, which is the limit as n goes to infinity of this sum, we can express this as a definite integral, because Riemann sums turn into definite integrals. And it's the integral from a to b of pi r of x squared dx. So basically, to find the volume of this region, which is this expression right here, you just take the sum, an infinite sum, of all these cylinders that are infinitely skinny and whose volume is pi r squared h. But since they're on their sides, h is dx, is infinitely skinny. So it's kind of like, it's almost kind of like if you had a bunch of CDs and you use these CDs to approximate volume. You have a bunch of super thin cylinders and you use those to approximate the overall volume. And this is if the axis of revolution is horizontal. So for a horizontal axis of revolution, this is the volume. If the axis of revolution was vertical, and again, as you watch this at home, make sure to press pause if I'm going too fast. But if the axis of revolution is vertical, then everything is in terms of y. Why that is so, no pun intended. Let's say we have some function that is now on like x equals f of y. We're going from C until D, this region right here, and then this is our axis of revolution. Well now, since we're going this way, these will be all of our rectangles, because you always line your rectangles up in the same direction as the axis of revolution. So when the axis of revolution was horizontal, we line up the rectangles along that way. When the axis of revolution is vertical, you just kind of stack up your rectangles along that way. And so now the height of all these cylinders is going to be the change in y. And the radius is going to be a function of y. So vertical, you are in terms of y. Okay, let's check out some examples.